Logs. What are logs? Well, let's have a think. Could be... Oh, no, it's not that either. What we mean by logs is... Go away. What we mean by logs is logarithms. So what is a logarithm? Well, let's take a simple example. 125 is the result of, is equals to 5 cubed, 5 to the power of 3. 125 equals 5 to the power of 3. Well, that is, if we twist things around, another way of looking at that is to say that 3 is equal to log to the base 5 of 125. Okay? Now the base bit is that bit there. Okay? That is your base. Okay? Note that that's important with logarithms to say the base of, although in actual fact it turns out that most of the time we have some bases that we tend to stick with. For example, 10, or what's called a natural base, or 2. But in actual fact, theoretically, you could have any base you like. In this case, the base is 5. Now, logarithms, why are we doing them in engineering? Well, what they do is they allow us to deal with small and large signals. So, for example, a little tiny whisper in the ear is one thing, but a great big roaring jet, thank you very much, is quite another. The point is we can plot both of these sound levels on the same to deal with small and large signals. So, for example, a little tiny whisper in the ear is one thing, but a great big roaring jet, thank you very much, is quite another. It's not just sound, of course, that's just one example. This is a TV amplifier bought from the Argos shop. They actually say the gain, the increase, is 20 dB. 20 dB is equal to 10 times log to the base 10 of 100. On Argos's website, where they say it has a 20 dB gain, what they mean is it's 100 times increase from the original signal. So how would you calculate a log? Well, for this you need a scientific calculator. So we've gone to the calculator on Google, and here's what we can see. And just here is log to the base 10, which is your standard one, so it just says log. And the other one it's got on here is ln, and that is called the natural log. And that is to the base of 2.718. Now most of the time you're going to just use log. Unsurprisingly, it's just log. If we had to work out, for example, log of 100, we just type in log of 100 brackets equals, and we get 2. Brilliant, that's correct. So what would the log of 1,000 be? Log 1,000 brackets equals 3. Excellent, that's correct. Now let's do, for example, log of, say, 1,000,000. Million's got 6 noughts. 1, 2, 3, 4, 5, 6. That's log of 1,000,000. What's that going to be? 6. Brilliant. And that's exactly what you expect, as you can see. Log to the base 10 of 100 is 2. Log to the base 10 of 1,000 is 3. And log to the base 10 of 1,000,000 is 6. So that's a quick description of logarithms and how they occur in engineering. But what we really need to do is understand how to manipulate and use them. And for that we need the laws of logarithms. So what I'm going to do, I'm just going to list them, and I'd like you to just write them down. Okay, so this is them here. So if you just scribble those down, stick me on pause. When we start off again, I'll carry on and go into these a little bit more detail. Okay, so see you in a mo. Okay, so you've got down that little list of the laws of logarithms. Note that the log implied here could be to any base. That said, typically it's base 10. So we've got log brackets of a plus log brackets of b is equal to log of a times b. For example, let's try log to the base 10 of 2 plus log to the base 10 of 3. What would that be? So we have log of 2 plus log of 3, and that means really log to the base 10 of 2 plus log to the base 10 of 3. And log to the base 10 of 2, if we work that out, is 0.301, and log to the base 10 of 3 is 0.477. Add them together and we get 0.778. So log 2 plus log 3 is 0.778. Now what we want to do is take log of 2 times 3, and that's log of 6. Log of 6 is also 0.778. So what we've done is successfully demonstrated that indeed log of a plus log of b is equal to log of a times b. Okay, now on to the second law of logarithms. So this time we've got log a minus log b, and that means the same as log a divided by b. So what we're going to do this time is we're going to say what happens if we take log to the base 10 of 6 minus log to the base 10 of 3. Does that equal log to the base 10 of 2? Okay, so we have log of 6 minus log of 3, and that's obviously log to the base 10 of 6 minus log to the base 10 of 3. And if we calculate those, what we find is log to the base 10 of 6 is 0.778 and log to the base 10 of 3 is 0.477. Subtract the two, we end up with 0.301. So what we can say from that is that log of 6 minus log of 3 equals 0.301. The question is log of 6 divided by 3, which is log of 2, also equal to 0.301? And indeed it is. So we successfully demonstrated that log of a minus log of b equals log of a divided by b. So that leads us to our third law of logarithms, which is n log of a is equal to log a to the power of n. So let's see if that's true. So we're going to put some numbers in. So for example, 2 times log of 3, and that's log to the base 10 for example, does that equal log to the base 10 of 3 to the power of 2, or 3 squared? Well, 3 squared is 9. So the question is, does 2 times the log to the base 10 of 3 equal log to the base 10 of 9? We have n times log of a equals log a to the power of n. Well, let's test this out. So 2 times log of 3 equals log of 3 to the power of 2, or log of 9. The question is 2 times log of 3 equal to the log of 9? Well, 2 times log of 3 is 2 times 0.477, which equals 0.954, and the log of 9 equals 0.954. So indeed we've demonstrated successfully that n times log of a equals log a to the power of n. Okay, so that leads us to our fourth and last law of logarithms. Now this one's slightly different from the others because it allows us to convert from one base to another. So for example, if we're working in base 10, which is what's on our calculator, and we need to work out something in base 2, this law allows us to do it. So let's just have a quick look at the law. So the law is that the log to the base a of m is equal to log to the base b of m divided by log to the base b of a. Okay, so now let's put some numbers in for those. Let's start off with log to the base 2 of 1024. Well, log to the base 10 of 1024 is 3.0103, and log to the base 10 of 2 is 0.30103. and if we divide one by the other, then we get 10. So we can see that log to the base 2 of 1024 is 10. And we can check that because 2 to the power of 10 is indeed 1024, so that is indeed true. That demonstrates that log to the base a of m equals log to the base b of m divided by log to the base b of a. Now there are two more important results to be aware of. The first one is that log to the base m of m equals 1. It's always equal to 1. Why is that so? Well, let's just look at a couple of examples. Log to the base 10 of 10 equals 1, and also log to the base 8 of 8 equals 1. That must be the case because 10 to the power of 1 equals 10, 8 to the power of 1 equals 8, indeed m to the power of 1 equals m. So therefore we can see that log to the base m of m equals 1. And the last important result we need to be aware of is that log to the base m of 1 is always equal to 0. Why is that the case? Well, log to the base 10 of 1 equals 0, for example, and log to the base 8 of 1 equals 0, for example, because 10 to the power of 0 equals 1, 8 to the power of 0 equals 1, and indeed m to the power of 0 equals 1. So we successfully demonstrated that log to the base m of 1 is always equal to 0. So that concludes our whistle-stop tour on logarithms. I hope that's been helpful. I hope I've put enough examples in there to help you. If you need any more, please let me know. Send me a line on Twitter or whatever you like, or email me, and I'll try and do the best I can to give you a bit more information. This little video, as I said at the beginning, should fit in with the previous material on P1, which is indices and exponentials and exponential growth. So you should watch all those three together, but you should have enough material to be able to have a good go at your P1 now. Okay, let me know how it goes. Best of luck. See you next time.